Okay, welcome back to discrete math. This is section 10.2. There is some vocabulary at the beginning of this section that I actually already went over in a video for section 10.1. So if you have questions about that, you can go check out those videos again, or of course always you can reach out to me or come to office hours or something. But I want to begin this lesson with something called the handshake theorem. There is a funny parlor trick that you can do that relates to this theorem, and it works like this. You're with a bunch of friends, or you're in a classroom with a bunch of students or something, and you tell everybody just walk around and just shake hands with each other. Doesn't matter how many times, but you're going to count how many times. Okay, and it doesn't matter with whom you shake hands as long as you're counting the number of times you shake hands. And if you can't shake hands with the same person twice, then you need to count that twice. And if you shake hands with yourself, which you could do technically, you would count that twice as well because there's two hands involved, well, your left and your right. So everybody counts the number of times they shake hands, and then you say, okay, stop. And then say, I'm going to ask anybody who shook hands an odd number of times to raise their hand. And I predict it's going to be an even number of people. And then they do it, and it should be an even number of people as long as they did it right. And then they'll go, ooh, wow, how do you know that? Well, it comes from this thing called the handshake theorem, because what you're doing when everybody's going around and shaking hands is the people are acting like vertices and the handshakes are like edges. So you're creating a graph as you do that. Um, the handshake theorem says we have a graph G with vertex set V and edge set E, and let's just have that be undirected. When you go around and shake hands, that's an undirected graph. Right? Okay, if we have any undirected graph, then we can say a few things about this. One of the things we can say is that the number of vertices of odd degree is guaranteed to be even. So there's an even number of vertices of odd degree. And that is really more of a corollary to the main point here, which is saying that the total degree sum, that would be adding up all of the degrees of all the vertices in the graph, is even. Now, if you add up a bunch of numbers and you get an even number, then you can't have had an odd number of numbers that were odd. That sounds funny to say, but think about that for a moment. If you have an odd number of odd numbers and you're adding them up, then you will result in an odd number. But if you have an even number of odd numbers and you add them up, you can get an even. So that's kind of a fallout from that. Now, in particular, scroll up a little bit here. In particular, we can say more precisely what that degree sum is going to be. So here's the notation. Summing, right? This is our sum notation we use in calculus. Summing over all elements of the vertex set. So we're going to sum over every v, lowercase v, an element of capital V. So these are all the vertices. And what we're summing is the degree of that vertex, of each vertex. So this is adding up all of the degrees of the vertices. And we can say that that will be exactly 2 times E, where E is equal to the number of edges, or the cardinality of the edge set. So that's very precise now. Okay, this is really the heart of the handshake theorem right here. That adding up all the degrees gives you twice the number of edges, and there's a very simple explanation for why this happens. And the reason is that for every edge in the graph, that edge has 2 endpoints. So it contributes to the total degree sum exactly twice, once for each end. Right? So when you're adding up all of the degrees of all of the vertices, it's like adding up how many for each edge. It's like adding exactly 2, right? One for each endpoint, hence twice the number of edges. So very simple explanation for this. But it does allow us to do some kind of neat things. Um, first of all, let's go over an example. I'm going to scroll over here. Let's do an example. I'm going to pause and draw a graph. Okay, there we go. So there's a graph. And for this graph, I've got the vertices just labeled A, B, C, D, all right? And then I've got some edges. First thing I'm going to do here is count how many edges there are. So what is the value of E? E would be the number of edges here. So let's look. I've got one over here. Oops, that's going to make it look like two. Shoot, that's not going to work. Okay, so I've got one edge here. I've got this loop. Got another edge that connects A to C, so that's 3 so far. Got an edge here that goes B to D, that's 4. And I have 5, 6. So that's 6. There we go. So now, if I want to figure out the total degree of all of these vertices, this is going to be the degree of A plus the degree of B plus the degree of C plus the degree of D. Going through and looking at my graph, I can look to see what those degrees are equal to. For A, I've got exactly 2 edges leading out of A there, so that's a degree of 2. For B, I have 1, 2, and then this loop counts twice, once for each. So 1, 2, 3, 4. 4. For C, here I have 3. And for D, I also have 3. Note, only 2 of these are odd, right? And 2 is an even number, right? So there's part of our theorem. And then this total sum here is 6, 9, 10, 11, 12. There we go. And that is exactly 2 times 6. So that's just demonstrating the handshake theorem, okay, with this particular graph. So one of the things you can do with this is you can make inferences from limited information. So for example, if you know this information, that G has 9 vertices, each of degree, say, 4. If you've got 9 vertices, each of degree 4, then you can say the degree sum is going to be 9 times 4, right? 9 vertices, each of degree 4, so I'll add them all up. 9 times 4, 36. And then by the handshake theorem, we know that we can say exactly how many edges there are in this graph without having sort of counted them, right? Without even looking at a picture of it, we can know number of edges. It's going to be exactly half of that 36, or 16. All right. So that's the handshake theorem. There are a few problems in the textbook where you can use the handshake theorem to help you prove some identities about like the number of edges and the number of vertices in certain types of graphs. Okay, so that'll come up on a couple of proof problems.